Hello everyone. I want to review a paper about a simulation of melted uranium dioxide on a 90-degree band channel by using the moving particle semi-implicit method for reactor core catcher development by Yakobus Yulianto, Asril Pramutadi Andi Mustari, and Muhammad Rizky Arbi, 2024. So this paper will simulate about a European pressurized reactor, especially in core catcher, where is a 90-degree band channel in here. In this study, they simulate the flow of uranium dioxide liquid inside a channel to observe its dynamic as it passes through a 90-degree band. We can see in the figure 2, the band of 90-degree band is what is a cycle. And in this paper, it will investigate crucial parameters including surface level, the magnitude of velocity, flow rate, pressure distribution, Reynolds number, and fluid number during the flow of melted uranium dioxide at 3000 degrees C and 3400 degrees C of temperature inside the band. The method is a simulation using moving particle semi-implicit or MPS. This model is used model Wood and Wang experiment in 2050 about modeling dam break flow in channel with 90-degree band using alternating direction implicit based curvilinear hydrodynamic force solver. This setup is same with that experiment, and there is three material they investigate in this paper. There is freshwater, uranium dioxide in 3000 degrees C, and uranium dioxide 3400 degrees C. And there is a four position that they will observe the simulation. The label is A, B, C, and D with position in the table 2. The simulation is first, the simulation is compare the simulation and the experiment from Wood and Wang. This is the simulation of freshwater. In the figure 5 and figure 6, we can see the simulation. We can see the flow water inside the channel, and the data is compared with the experiment from Wood and Wang, and we can see in figure 7 and figure 8 the simulation have a good agreement with that experiment. So because the data have a good agreement, then the simulation is next to the next material, that is uranium dioxide in 3000 degrees C and 3400 degrees C. This is the data from the simulation. We can see that the comparison of surface level in four position between water and uranium dioxide in two temperature have a similar pattern. We can see too in figure 10 and figure 11 that flow of uranium dioxide inside the channel over time for 3000 degrees C and 3400 degrees C is a similar pattern, but uranium dioxide in 3400 degrees C can reach the end of the band faster than the 3000 degrees C, about 0.05 seconds. This is the another result for a time step of reflected wave phenomenon. We can see that the pattern from freshwater and uranium dioxide is same. The flow will flowing to the left and collide with the wall in the band, and then it will reflected. It's the same phenomenon. And if we see the flow rates for each gauge for water and uranium dioxide, it's show us the same pattern between water and uranium dioxide. And then for magnitude of velocity in each gauge, we can see water and uranium dioxide have a similar pattern, but in a gauge A and gauge D, there is abnormality where water and uranium dioxide have a big difference. Next is pressure distribution for fresh water and uranium dioxide. We can see that the pressure distribution, the highest pressure is in the dam and in the wall, uh, and in the band, in the 90-degree band. It can be like that because of mass concentration in there. Uh, Next is Freud numbers. We can see that Freud numbers for water and uranium dioxide have a similar pattern, but there is an abnormality in gauge A and gauge D. The Freud number is have correlating with how high the fluid jump and flow. A higher fluid number, it means a higher uh, fluid can jump in the flow. And in the figure 19, there is a velocity factor of uranium dioxide inside the channel over time. We can see that in the 90-degree band in the wall, of course, we can see that the velocity factor is smaller than in another position. It's have correlation with the pressure too, because it will make the mass distribution around the wall. And then there is a Reynolds number and have correlation between flow rates and Reynolds number. That increasing of flow rates will increase the Reynolds number for water and uranium dioxide because there is same pattern. For discussion, when particle size is 0.02 meter or the smallest particle size in this study, the water depth at the chosen position is close to the experiment result because of there is because a particle where they simulate is also have a bigger number. So this will close to the experiment result. And then the decrease in velocity decrease the level, the surface level, because uh, the velocity have a correlation with surface level in the simulation. The third is when the reflective velocity is larger than the mainstream velocity, the average velocity decrease. It's because the velocity of flow, the fluid flow is collide with the mainstream of the reflected flow. Then the velocity is become smaller. Uh, the fourth one is an increase in the observed flow rate correspond to an increase in the Reynolds number produced. It's like what I said when we see the flow, when we see the figure, that the increasing of flow rates have correlation with Reynolds number, and it's a positive correlation. High increases of flow rate will increase the Reynolds number. For conclusion, the obtained results showed that there was a positive agreement between the simulation and experiment for high Reynolds number gravity inertia regime and ignoring any cooling or solidification phenomena. In the isothermal scenario, when the cooling impact is disregarded, the uranium dioxide flow within the 90-degree band is comparable to that of fresh water for gravity inertial regime in higher Reynolds number. 3. The more particles used, the closer the results are to experiment. 4. The mass accumulation at the band causes a stagnation point at the band and increase the pressure on the band wall. And 5th, when the Reynolds number is high and the flow is typically turbulent, the fluid number becomes a more significant indicator of flow characteristics. That's all. Thank you.